Good afternoon. Good afternoon, Signal. How are you doing? Yeah! After lunch sessions are always the best ones. Welcome. Today we're going to speak about how Twilio builds Twilio, what happens behind the scenes. We have a packed agenda. We're going to crank up the pace a little bit. But before we do that, please mark down the number. Your feedback is really important for us. You'll see it also at the end when we do a Q&A. Have a few minutes for that. But please do give us feedback. It's important. So what we will cover today. We've been operating cloud services for quite a few years now. Today is this session is about what's happening behind the scenes. We heard Dr. Vogel speak about services. We're going to touch about those services, and it really builds based on that. During those years, when we have operated Twilio, we have learned quite a few things. This session is about sharing those learnings, and maybe you can use some of those learnings within your development. Its focus is on scale. Scale from two aspects. First aspect, how to scale the organization, but also how to scale the architecture and technology. But first of all, when this works, what we do. We already heard the numbers. What's our scale that we operate in? It's 700,000 developers. Our product operates in 200 countries globally. We have more than hundreds of carrier interconnections. Probably next year it will be thousands. We do this all globally. It's 24/7. 24/7 operations. Our customer base is global. So are we. We operate in 7 different regions, in 28 different data centers, guaranteeing that the presence and failover is there. Today, Twilio platform does more than 4 billion API calls monthly. Those 4 billion calls are supported by 350 microservices. Werner spoke about what Amazon has, like 800 services. Well, we have some of the microservices, some of them are maxi services that we need to break out into microservices. That runs on thousands of instances, and every second we initiate thousands of new calls and messages that go through Twilio platform. In order to do that, we did this with more than 20 product teams who deploy new code to production 40 times a day. So Twilio gets better 40 times a day. We have achieved a feature velocity, which basically every 6 days we ship a new major product to the market. We have kept that pace since last August, and we keep accelerating. So how do you get to that? There are 2 units of scale. One unit of scale for us is a service, already mentioned by Dr. Vogels. Focus is to avoid monoliths, break code into smaller repos, operate the services separately. Define clear boundaries between services, and put an SLA on them. SLA is defined by interfaces, availability requirements, but also performance. Don't measure average, measure P99. Measure the outliers, that's what's important. Also 500, instrument your service, that's important. And always expect upstream failure and downstream failure. Everything will fail at some point in time. Peter will speak about failures and how do you handle them, but I expect that when you build. And also build services using self-service mindset. Don't just offer a service to others, just create it in a way that other teams can consume it easily. Second unit of scale is a product team. Each product team is self-contained, empowered, and accountable for the services. They think like an owner. The product team lead should be like a CEO of the company. We have more than 20 companies inside of the company, and with a clear mission, with a clear purpose. They build, test, deploy, and operate the service independently from each other. There's only one backlog per team, which includes operational issues, bugs, issues, and new features in that. That keeps your focus on operational excellence. Each team can select There are tools and working methods that suit the team. There's no top-down, this is the way to go. You can alter that because it's important to, if you're an owner, you select the best tool for a job. The key thing here is the ability to ship independently. Each team is able to ship independently. So really, organization follows the architecture, not vice versa. Based on architecture, what we have, the service that we have, we form teams. So services and product teams together are the team organization that makes Twilio. We prefer APIs over meetings if that's not clear yet. So we provide APIs to you. We internally also are heavily API-fied. If a team finds itself in cross-team panic section, like too much communication, the best way is to do it. Break the service into APIs, serviceify it, build APIs, and let others consume that. And really, when you have that API approach also within the organization, experimentation is really an investment decision. Should we do new product X? You have the infrastructure, you have the platform, and you just allocate people onto those opportunities. And yeah, the main thing is, in order for this to work, you need to have a resilient base platform for deployments. The biggest team, so one key thing is also, each of the services is owned by one team. There's no cross-sharing. There's clear ownership. The biggest team owns, like, I think 35 services, which is pretty large team. The smallest one owns 2. The small team rule, like Amazon has the 2 pizza team rule, we have automatic split at 10 people. If it's more than 10 people, the communication usually becomes too big of overhead. We break them out into smaller backlogs, smaller teams, fund them separately, and there they go. So growth happens. We're always excited to learn what you build, and we sometimes see huge loads coming in. So that's why everything that we build, everything that we ship needs to scale at least 10x. And that needs to scale horizontally. Stateless services are really easy to scale horizontally. You cannot have spoofs in your mix. Think globally from the start. That's our customer base is global, your customers are global, everything needs to be global. We're going to talk about architecture and some of the failure modes that can happen. When you open up an API to a to a global user base, you will see all kinds of use cases. You need to plan for capacity that you have for use cases, but also burstability. If a radio DJ in Brazil says in a public radio, one of the most popular one, that, hey, call this number and you get the extra gas credit or something like that. Believe me, tens of thousands of people will call the same minute, the same number. So serving 1 million calls or 1 million messages within a month is one technical challenge to address. But serving that same 1 million calls or 1 million messages within 1 minute, it's a whole different scalability and different infrastructure you need for that. You need to anticipate failure at every step. Real-time communications adds another layer of complexity into the mix. You need to be, like, latency becomes really important, because if a message arrives maybe a second later, you can deal with this. But if a voice packet arrives more than half a second later, usually like, hey, are you there? Are you there? You probably all have had that situation. You need to be really close to the customer. And also when you open up APIs to the public, bad uses, because fraudsters will come. Criminals will come to use. So you need to build architecture that supports or automatically detects the failure cases, the fraud cases. So with that, we'll dig into 2 topics today. How to plan for failure, actually how to design for failure. And with that, I would introduce Peter Shafton to walk us through that. Thank you.
Thanks, Ed. So normally if your boss invites you to come on stage in front of a slide labeled failure, you would take that personally. I see it as a badge of honor. As a software engineer, we design for failure. We expect failure. We're taught to write code defensively. to expect bagged inputs to our functions. But as you scale up into distributed systems, the failures get much different. So you can see a failure here. This is if a gas pipeline goes down in San Mateo and knocks out your house. That could happen to the Amazon data center. Hopefully it won't. For us, what will fail? Well, those of you that know, anything in the system can go. If you're dealing with real hardware, the drives can fail, the system can kernel panic or reboot. You can lose your network. The software itself can crash. For us, connectivity to our carriers can go down. We can lose connectivity to one or all carriers. And then the Amazon systems that we ourselves rely upon are obviously a possibility for failure. S3, SQS, even the AZ that we are hosting our services in. So the big question for us is, how do we know that something failed? So we know it's happened, but what happened? And that's not always easy to detect from the outside. We use 3 systems mostly for monitoring: Nagios, Rollbar, and Stackdriver. These let us know if one of the services has gone down, if one of the pieces of software is not acting as we expect. When we talk about the carriers, we have a different class of problems. So we couldn't just go and grab an open source tool that told us carriers are misbehaving, that SIP traffic isn't as we would expect it. So we had to build our own. CallMeta and Victorinox are 2 systems that we've built that allow us to see not only at a macro level what's happening across all of our carriers or a given region, but to drill down into a specific call and see what happened on that call. We have service level monitoring. We use health checks that we built that allow us to see if any single service is handling more or less traffic than another, something is misbehaving. We have application monitoring with anomaly detection. We can tell if one service is handling a lot more traffic than another, or if services drop down. So if we're failing to send out a message, that's fairly easy to detect. A lack of an inbound message is a little trickier, right? Should there have been a message coming into us or not? We don't really know at any given time. But we use anomalies to sort of tell us traffic is different than the pattern we would expect. Fraud detection. We have a tool called Kermit the Fraud that allows us to help detect fraud coming into our system or going out through our system. People that are using your accounts or your phone numbers in ways we wouldn't expect them to. That's a trigger to us. We have end-to-end testing. This lets us know if something that from the end user side isn't working as expected. From inside, it's fairly easy to tell, but if traffic from your endpoint is failing, we have to be able to detect that and notice that as well. We have something called the Feedback API. If you guys haven't seen it, you should take a look. It allows you to tell us when things aren't going as you would expect. If you're having voice quality issues and things like that, that allows us to see even more quickly if something's anomalous on your side that we maybe didn't detect ourselves. So once we've detected failure, the real key to doing this well is designing around failure. So we know things are going to fail. How do we deal with it? We want to fail gracefully, right? If something has failed, we want to stop using that service quickly, route around it. As Oid pointed out, we don't have a lot of time with a phone call. We can't be leaving things for a long time and going a different path. We have to fail quickly and gracefully. We have to make use of all the availability zones that are available to us. So if we put a service up, we've got to spread it everywhere. Anything can go down. We've got to have redundancy. We have highly available distributed caches. So if you think about the way we access data, the information we need to know your account, we need to know who owns the phone number. All that data lives in data stores. Bob will talk more about scaling that layer of our system, but we have caches in front of those things that we can handle outages at the data layer. The caches themselves have to be highly available. And when in awful, we will retry. So if we tried a carrier, it didn't work, we'll go to another carrier. If we tried a region, it didn't work, we'll go to another region. Whatever we can do to guarantee we get service. So one of the rules that we have is we're multi-AZ. Anything you stand up, 3 AZs or more. Some of the biggest outages in the history of using AWS is because people were only in a single AZ. If you lose that AZ, everything's gone. So you got to route around that. Amazon is an amazing operator. Those of us who have been on it for a while, and for me it's been almost 4 years. Everything fails. DNS fails, networks fail, ELBs, the things you rely upon, S3, they all are prone to failure, right? They've done a good job creating redundancy, but you've got to be prepared to handle those failures and route around them. So how do we mitigate failures? We mentioned the multi-AZ. Our rule is you've got to be in 3 AZs if you stand up a service. We also use a highly available queues. So you think about when you guys are sending messages or phone calls to us to send out, we have queues in front of the systems that send those messages out. If we have latencies in our database systems. We have latencies in the call setting systems. We have to be able to queue up those messages. We have to be able to send them out in an efficient manner and know that even if we lose the queues, that we can recover all of those things. I mentioned the caches earlier. Those are in front of the databases. We also use Amazon's SQS and S3. That allows us to store messages or longer-term storage. You can think about us using it for recordings. You can think about us queuing billing events, things like that we'll use Amazon services for. We use HA proxy a lot. It allows us to do hardware and software load balancing, so we can detect failures of downstream services. We can route around those. We have our own software health check systems that do that as well. That allows us to have really quick reactions to stuff. And circuit breakers. So if something fails, lock it off quickly, move on to the next service. So the testing is another important part of what we do. At the simplest level, we're doing unit tests. I think everybody's familiar with that. You stand up a service, you make sure each of the low-level components work. We do integration tests. We're sticking two things together. We got to make sure we both agreed to the contract, right? One person wrote the API, one other team wrote against the API. Did we both agree the same way? Longevity testing. So for us, if you're going to stand up a voice service, calls are going to be on that server for 4 hours after you take it out of rotation. It means we can't have a service that leaks or loses memory over time. It's got to be able to stay up, and it's got to be able to stay up for months on end without crashing. So for us, longevity tests are important. Load testing, figuring out when and how things are going to break before you guys find it for us. We want to know that. We want to know how many calls we can put on a box. We want to know how many messages we can send through a box before it falls over. So this is key for us. We built our own black box testers that allow us to create call simulations, go through all the scenarios using our APIs itself. They don't take advantage of anything they know about the internal systems. They just interact with our APIs directly, and we're making hundreds and hundreds of phone calls all day long. We have end-to-end testers, as I mentioned. Those notify us outages at the edges, right? If we're having issues with connectivity from certain regions, the end-to-end testers let us know that. So how do we maintain velocity with a team that's building and doing all this testing? So the key is to have a bunch of safety nets, right? You think about it, somebody walking a tightrope, if they got a net beneath them, they can walk a lot faster than if they are going to fall. So for us, Shadow is one tool we use. It allows us to stand up another service in production, take the full load of production traffic, but not affect anything downstream. We can see how it behaves. We can send all the API requests through it. We'll know exactly what's going on. We use Canary, so we can bring up a single service or a single node, send just a small portion of traffic through it, and see what it does and how it reacts. Obviously, we've tested before we got there, but sometimes things are different in production, and you have to see that live. We do gradual rollouts, so we can come up with a new feature. We can roll it just to a subclass of our customers, roll it on slowly over time, and then if it seems like it's working the way we would expect, handling load the way we would expect, we'll roll it all the way out. We have feature flags, so we can turn on and off certain capabilities within the apps, and we have account flags. This allows us to give certain features to certain customers or change features off for certain customers if their behaviors or use cases mean that it's problematic for them. This is a lot of flexibility for us. And so each of the teams can deploy independently. They've got their own APIs, we've got our SLAs we hold to, and we can roll out and roll back independently as teams, and allows us to go very, very quickly. As Oit mentioned, we're doing more than 40 deploys a day sometimes, and it really just allows us to go quickly and with confidence. So the challenges of real time. Oit mentioned this. One of the issues we deal with is latency and jitter of voice packets is really important to us. We have to keep tabs on that. We've got to know what we're doing, and we've got to protect against it. We can lose packets, we can have drop packets, we can burst and jitter due to network behaviors, carriers can misbehave, machines can have problems, CPU overloading, hardware failures, mics and whatnot. So the way we get around that is with a lot of teams and a lot of tools. We have a carrier operations team. They allow us to tell us which carriers are doing what, contact the carriers directly when there's problems. We have automatic routing around failures. We have global media pops, so we hastily route the media in each of the edges around the world so we can get audio as close as possible to the endpoints. And then we use CallMeta and Victorix, as I mentioned, tools that allow us to dig into what's going on directly. And with that, I'm going to give Bob a chance to come up and talk to us how to do capacity at scale.
Thank you. Hello. So let's talk about how we scale up a system to meet the capacity needs of the organization. Where's the problem? This is an old familiar slide from one of our co-founders, Evan Cook, saying that the problem isn't the stateless services that you can scale out horizontally easily, you just boot more machines. The problems usually boil down to data persistence problems, and that's the most interesting and the most difficult part to scale to meet performance needs. So where does that state live? It's not just There it goes. It's not just in your relational database. Your state can live all over the system. So you've got your SQL databases, any queues, any files on disk, any key value stores that you have around. These are all places where your data is living transactionally, and that state has to be highly available, fault tolerant, and be able to scale up with the organization. But let's start with where many people start and where Twilio started with the relational database system. There it goes. So how you usually start is you build out a database, you have the other systems, your other clients talking to it directly. This is the easiest way to build it up. When things start slowing down, you can shard that functionally, so you take different parts of different tables and move them to different machines. At some point, you get to a point where that one storage solution, it's not a functional split anymore, and it's not meeting all your needs. One system cannot fulfill everything. We saw this with our in-flight, with our calls and SMSs. You have the two functional or two areas where you have different characteristics on how you're accessing the data. One is on the in-flight side, so when a call is in progress, there are many reads and writes happening as the state is changing frequently, and also when the message is in flight, there's different statuses that are occurring. And then there's the long-term historical view, which is basically write once, read occasionally. This is where customers can come in and look after the fact at what happened, but you need to scale that more for size than for throughput. So how are you going to change out and meet these needs when you're all talking directly to the database? The answer, of course, is that you don't. You can move to, I'm really having trouble with this. There we go. So you put a data service in front of it, and that talks to your storage. You then move all your clients to talk to that storage service. And then that's the only thing talking to the storage underneath. So now you can swap out that storage with different technologies. You can shard it. And the only thing that needs to know about these changes is the data service that the clients are talking to. So this is service-oriented architecture. And it's a way that you can change out that storage to meet your needs. So how this looks in practice is this. So this is kind of a high-level block diagram of the in-flight, post-flight split. You can see that we put services in front of them, split out those data stores so that we can shard out for size on the post-flight system. The in-flight system is a smaller window of time. You can do high transaction rates there, and you can move to more memory-based things or whatever technology is going to work better for meeting the needs of that system. And what we saw here is that as we're growing very quickly, the size requirements are growing fast as well. The time to in between sharding was 6 months, 3 months, monthly. It grows very fast, but you can scale out horizontally that way because you've got a service in front of it that's handling all the talking to that storage system. And also, now that we have this piece of technology, we can use that to put in front of other stores as they become the bottleneck in the system, and we can servicify everything that hasn't been already. And anything new we build, we build this way. So what are some of the rules about how we deal with storage? As was mentioned earlier, we deploy like 40 times a day, sometimes peaking higher. We do not migrate data stores as often. So we keep those two systems separate. We keep logic and storage on completely separate instances, so we can deploy quickly on code, but our logic, with logic and our storage system is completely separate. So that's the rule there. We also don't want an issue in some piece of storage or some in the service that you're deploying to affect the storage that other people might need talking to that service. So what are the rules around MySQL? We use that a lot internally. We use it for what it's good for, which is basically rows with indexes on them. We don't use triggers, foreign keys, stored procs. We don't do any joins. All the joins we do in the software layer, because we're software people. That makes the functional sharding that we talked about easier, which is the easiest kind to do. Also, caching in front of everything also has to be highly available. So again, the rule is keeping logic separate from data. So what some other storage that we use, list them out here, OpenTXDB for metrics, Redshift Dynamo, Kinesis. The rule here is really what's the best operationalized tool for the job. So if you can take the time to, if it's worth it, to take the time to operationalize it and use it in the rest of the company, then we'll do that. We'll choose whatever is best for the task at hand. So how do we build out these changes without incurring any downtime? Since we are live 24/7 service, we don't have any maintenance windows. So we have to be able to build out changes in parallel. So we'll do this with database schema changes, any OS updates, software deployments, everything is even larger systems. Like we rewrote the entire billing system as a parallel path. We'd send messages down both channels, and at some point you can start moving accounts over or other piecemeal parts of the system. And you can also test that both are computing the same values. So you can debug the first system or the second system. Sometimes the second system finds bugs in the first. But that's how you can build it out and then move over without anyone noticing that you're doing this under the covers. Service APIs internally make this possible. So the rule here is building out in parallel and then migrating it in pieces. So how do we actually do the database part of that? So a couple years ago, we took on, it used to be done with a lot of scripting and manual labor. We took the time to kind of Twilio wrapper, put a Twilio wrapper around the MySQL High Availability Project, MHA. And we've made that very easy for all teams to use. So that means the teams can deploy their schema changes in parallel. They can very easily run the pivot system to move from one master to another slave that has the new changes on it without anyone noticing. We've been able to iterate on that, gotten the kind of downtime critical section to 2 seconds, and with all the retries on the system, that goes unnoticed. There's similar kind of scripting for the Redis clusters that we run internally. Okay, so what are the key takeaways from this? We have the ownership by small teams, so they can iterate and deploy code independently. Small stateless services that share nothing in multiple AZs and regions to handle for failures and issues. Plan out your storage with care because that's where your scaling issues are going to happen. And hide them behind services so you can change it in the future. Gives you a lot more flexibility. You want to operate any of the operations that you're going to be doing, and then you can iterate on that. And finally, build out any changes in parallel and then be able to migrate pieces of them. And with that, are there any questions? Thank you.
Remember the feedback. Thank you. I think we are able to take few questions.
Don't be shy.
Everything is clear as day.
So you mentioned high availability and failover. How do you deal with voice servers for this? Like if a call is hosted on a specific voice server, that server goes down, do you lose the call or do you have some mechanism for failing that over?
It's a little tricky, is the short answer. The key is to separate signaling and media so that the signaling goes through a single node, the media is through a separate node, you can fail over. That's sort of the key to doing it. But it's complicated to do, and it's complicated to do globally when you've got calls going through multiple nodes. If you ever look at our SIP traffic internally, there are times when we bounce through 7 or 8 nodes with the SIP traffic alone, and voice traffic, the RTP can travel through multiple nodes as well. We do some of it in some places. Not all the systems are set up that way. It depends. You heard him talk about this morning about rolling out the conference GLL. That is a system where the SIP and the RTP are separated. Not all the systems are set up that way, but some of them are.
I was wondering, how do you deal with privacy and personal privacy from the user perspective?
Can you elaborate a little bit more?
Well, basically, I was watching a movie yesterday, Citizen 4, which is a documentary, and it's very real. It's something that I was concerned, how are we translating from, the privacy of the information we are collecting, and how are we doing, different from before?
So from technology perspective, it's segregating the access to all of those roles, encrypt everything, make sure that all the teams, all the data that we collect are stored in one place in one constricted area. That's the approach we're taking.
That's all the time we have for questions.
Thank you.
Thank you very
Come find
much.
us if you have any more.